Alright, so now the next one here, we have a simple one. So it's just we have an ideal gas with a volume of 1.6 centimeters cubed. T equals 20 degrees Celsius, which is equal to 293.15 Kelvin. So that's just adding 273.15. And at atmospheric pressure, so our pressure is 101.325 times 10 to the 3 pascals. So our volume is, multiply this by 1 times 10 to the minus 2 centimeters per meter cubed. So that's 1.6 times 10 to the minus 6 meters cubed. Alright, so it wants us just to determine the number of moles. So so PV equals nRT. Rearranging this, we get N is PV over RT, which is 101.325 times 10 to the 3 pascals times our volume, 1.6 times 10 to the minus 6 meters cubed, over our gas constant, which for this I'm using 8.314, and this is in pascals meters cubed per mole Kelvin. And the temperature is 293.15 Kelvin. Okay, so we can see our units cancel here, giving us 6.6518 times 10 to the minus 5 moles. Okay, and then it wants to know the number of molecules. So the number of molecules would be this value times Avogadro's number. So 6.6518 times 10 to the minus 5 moles times 6.022 times 10 to the 23 1 over moles, which gives us 4.006 times 10 to the 19 molecules. Okay, so molecules isn't a real unit, so that's why the value is unitless. Alright, so looking at the solution here, we get about the same number of moles. The difference there would be probably my extra digits on the pressure, and my extra digits on the temperature. Okay, and then the number of moles would be multiplication by Avogadro's number. They get 3.99 times 10 to the 13, which looks like a calculator error to me, just because it should be roughly around the same range as if you add up the exponents here. So 23 plus 5 minus 5 is 18. Obviously is going to move depending on how these guys multiply. So it should be 18, 19, not 13. So I think there was a calculator mistake there. 4 times 10 to the 19. Mostly correct, just a small mistake at that point.